Meeting is being recorded.
I take of NCS 1K fit testing. So today we are going to have a basics of optics in L0 and L1. So before we go on the content, I'm going to show the picture, which is our topology in SIT. And after that picture, we will go on each of the components in detail. Okay. So this is the point-to-point topology in DCI, which we call Metro DCI. So it is nothing but a data center interconnect. Here, with respect to optical, when we talk, so there are multiple components. If you see on the left side in the diagram, there is a Nexus, ASR9K, and FRETA. So for optical testing, this is just an input for us. So we get the Ethernet output from these devices. When you see NCS 1004 here, which is nothing but a mux ponder. So this is the first you can say the first device from the optical side, mux ponder, which takes the Ethernet input and it gives an optical colored output. Okay, which you see lambda 1, lambda 2. These are the wavelengths. Okay, so this is the first device, mux ponder, what we will talk about. After these wavelengths goes in the fiber, there is a device called MD, which is nothing but a mux demux, which is the multiplexing all the wavelengths together one in a fiber, single fiber. Another device is an amplifier, which internal name is Mystique. Okay, so this is nothing but when signal travels in the fiber and the power gets reduced after some distance, so we amplify the signal. Okay, again, the same replica on the right side, it will pass through an amplifier. Then again, mux demux. So again, it will get demultiplexed, and the same wavelength will go on the NCS 1004 mux ponder, which will again take the wavelengths and it will convert back to the client Ethernet signal to the far end. Okay, so this is the end-to-end. We are in this diagram, if we have to understand, we are getting the Ethernet, we are converting into optical, we are putting all the wavelengths onto the fiber and just transporting from that for a long distance. Okay, so now we will get back to the slide.
Hey, Ankur.
Yeah.
Hey, on the topology, we also have 2K as an optical device, right? So this is only XR SIT profile and we are not doing any interop with that? Or will there be a separate CVT setup which will do?
We are doing, Prasad. There is another topology also. Okay, I have not shown that one. Okay, so this is the second topology, which has the same wavelengths. Same wavelengths are going via NCS 2K network. Okay, so here we are doing all the interop and GMPLS switching, etc.
Okay, and the other question, on both sides you have BOSOC, so what about Roscoe?
Yeah, so similar topology is there for Roscoe as well. Even the channels are mixed. Okay, in the same diagram we have Roscoe as well. So the Roscoe channels also go via the same 2K network.
Okay.
Okay. This is just a representation of the topology, what we do, okay, for BOSOC SIT or Roscoe SIT, right? But right now altogether we have one topology, which has Roscoe and BOSOC both channels together.
Thank you.
Okay. Okay, so let's get back to the slide. Yeah. So here we will just cover basics of optics. Anyways, we all are from communications, so it's very easy to understand what we do in optics different. And second is fiber optics, fiber types. So here we will discuss about different fiber types and properties or impairments in the fibers. Third one is DWDM system. So we will see the complete picture of DWDM system. Another is OTN. So we have a framer here, OTN, which is called Optical Transport Network. So here we will discuss about the OTN frame, OTN properties and all. Next is I'll talk about NCS 1K portfolio, which is very short, one slider, just to know about the product line for 1K optical size. Last one is set topology, what I have already shown. Okay, so when we discuss, when we start, right, optical communication, so why do we need optical? So as we know, the fastest medium in the universe, right, we have the light as the fastest medium, and optical fiber works on the principle of laser, okay, which is just a light amplification by the stimulated emission of radiation. So laser is the fastest medium, and we carry anything on the light is the fastest way to transport. Can you please mute somebody? Yeah. So yeah, so we get the higher bandwidth, we get the longer distances. So in the we work in three segments. One is metro DCI, another is long haul, and the last one is submarine, which is very new to Cisco. So long haul we consider like from the long distances, it can be 1,000, 2,000, 4,000 kilometers. The optics advantages are high bandwidth, longer distances. There is no electrical interference, and so security is one more thing when we move from copper to fiber, right? Okay. So optical communication system, when we talk there, so there are three things. One is transmitter, another is communication channel, third one is optical receiver. So on the transmitter side, we have to take care about three things, which is our output power, min max output power. Second thing is what wavelength we are carrying. Third is modulation type. So what kind of modulation scheme I'm using from the transmitter. For the communication channel, it's nothing but a fiber. So again, the layer 1 and layer 0 technology. So optical fiber, we have to take care about attenuation, dispersion, PMD, and nonlinearity. So these properties we will talk in next slides. What is attenuation, what is dispersion, and what is polarized mode dispersion. From the receiver, we have to take about sensitivity. What is my receiver sensitivity in particular port, optical port, or OSNR limit, which is optical signal to noise ratio. So that is also very important point for the any optical link. And another one is chromatic dispersion. Okay, so these are the points we will discuss in basic optics. So if I have to tell you simply the simple way of communication, right? So you see the torch, right? So it generates light, which goes via optical fiber. And here is a receiver, which is our eyes, right? So in the receiver, we have a photodiode, which reconstructs that electrical signal. Okay, so this is just a simple picture for the light, how the light travels. And on the light, we carry our digital data. Okay, so how far the light can go? As we know, light, when we switch on the torch, right? So there is some distance. At some distance, the light will get attenuated. That is called the power will reduce. So that is called attenuation, or the light will get spread. So when the light gets spread, that is called dispersion. Okay. So there can be two things in the laser power, right? There can be attenuation and there can be dispersion. Okay. So to understand this, we should know the basic of optical fiber. Okay, like how optical fiber is manufactured, what are the how is the core and cladding, right? So if you see that fiber picture in the cross-sectional diagram, right, in this one, so there's a center, right, which is called a core. On that core, there is a cladding. This is another encapsulation, and over that we see the plastic coating. So when we use the optical fiber in the labs, right? We might not go, if you're not an optical person, you might not go in that details. But as an optical understanding, you should know the basics. So the core is the one from where the light enters into the fiber. Okay. So there are a lot of physics inside it. When light enters at certain angle into the fiber, it gets totally internal reflected. So light is not traveling straight into the core. It is entering into the angle, so that the light will get totally internal reflected and will reach on the other end. Okay, so there are some properties like core is the glass material, cladding is another material. So there are refractive indexes. Okay, we'll not go in that detail, but these are the factors which will impact uh, into the uh, attenuation, dispersion, etc. Okay, so these are the three fiber types basically what we use. This is a standard G652 that is called non-dispersion shifted fiber. There's another G653 dispersion shifted fiber, and non-zero dispersion shifted fiber is G655. So there are three type of fiber which works on different. If you see zero dispersion at 1310, so normally we want some dispersion into the fiber to avoid the other effects in the laser, right? So we'll go to the attenuation. Attenuation is nothing but an optical power loss. Attenuation happens due to impurities like OH, metal ions, etc. in the fiber, limits the length of the communication. So attenuation is always based on the fiber length, right? So you can have some, if you have a 10-kilometer fiber, you might have some attenuation per kilometer, so that you will know when you use the fiber for this distance, whatever power you transmit, it will get attenuated within that length and you will receive that lesser power. Okay, so attenuation is one factor here. Okay, so if you see this graph, it has wavelength versus attenuation. So when you see there is a spectrum, okay, optical spectrum, where you see these attenuations are very low, between 1500 to 1600. So that is the reason all the optics, right? We use these wavelengths for our operational work. Okay, so these wavelengths are used mostly like from 1500 to 1600. That is called C band and L band in the spectrum. Okay, I'll talk about spectrum in next slide. So there is one thing which is attenuation, it is optical power loss. There's another one is dispersion, which is broadening of pulse. So how the dispersion occurs, right? So there can be multiple type of dispersions, which is first is material dispersion. So it can be a variation of refractive index of the core material as the function of optical wavelength, right? So I discussed about the core of the fiber, which is a glass. So due to that material also, variation of the refractive index, we can have a dispersion. So light can spread. Similarly, waveguide dispersion occurs when the propagation of light in the core and cladding layer differs. Third one is polarization mode. So there are two poles in the light. Fast and slow axis have a different group velocity. So pulse travels, and there might be a difference between these two polarization light. So there can be dispersion. Okay. So now we will go to chromatic dispersion.
Anchor, Anchor Len here. I have a small suggestion. Right? So since you are good with optics, you have to compare these. You are giving the terms, right? Whatever your terms, different type of dispersion, attenuations, and wavelength. And have you compare this to the real time where what is available in the market? What is they're using it? What is it? So those things will be help to us. Like, what we have three type of dispersion in in the fiber cable. What is we are using the lab? What is the customers are using it? What the technology is doing that market? What is the latest one? So those kind of information, if that will be added to this session, right? So that will be given more clarity to realize what we are doing and what, because these terms are only helpful when we are deeply work on fiber. So the group of people here is has the application level of fibers. They are doing it, and everybody is working on fibers, but we are not going to be involved much activities on that. So we have, if there is a comparison between the real time on the field, that will be help to us. You got my point, right?
Yeah, so I mean, these are the parameters what we use for the when we have to measure optics, right? I mean, end-to-end ports, right? So these are the properties which will get applied on the ports, right? You will have chromatic dispersion on the ports, so you should know that with which CD range I mean, you can use it right within the spectrum. Yeah, so I think, yeah, so are you looking for any, I mean, access the box and see the parameters like that?
No. Just I want to know that because we have these much parameters, right? In this question, we are telling about 3 variants, right? And as plus we have before we are seeing that nation, you are showing some kind of cables which is available in the dispersion. Based on the dispersion, there is a cable is available. So what is, see, WDM, DWDM. We know what is the difference between that. So what we are using it nowadays. So what is the advantage? So those kind of information which I am looking at. You see, even your parameter, we are trying to understand the real time application, real time working on that. That is the market. What the market is doing it. So that is, see, what you might read something else also, right? Instead of in the technical term, you might read, and that information also helpful to visualize us to read these things. So that is what my request
Got it.
is.
So, yeah, so idea is here to just to understand the parameters, basic parameters. Then we'll go to the topology, whatever our topology, and then we will, I'll explain like how these parameters are playing within the network.
That is what I'm doing. Yeah, thank you.
Okay, so the chromatic dispersion, simple definition again, like so material dispersion plus waveguide dispersion happens, and then chromatic dispersion. So we have different wavelengths traveling within the fiber, and those wavelengths reaches on the different time at the receiver. Okay, so due to that differentiate delay, you might have dispersion. Okay, so to avoid these dispersions, we have dispersion compensating modules which we can put it within the network or within the line card. Uh, there are fibers which are like dispersion compensation fibers. So these, see, normally these are the impairments in the network. What we have to fix it, right, to bring up the link performance. Okay. So next one is optical signal to noise ratio, which is another important point, and noise figure. So as I told you, right, when signal travels for the long distance, the power will get reduced, or it will get attenuated, right? So we need an amplifier in between, which is nothing but amplifying the power, right? Optical power. Okay, so during the amplification, uh, there are other effects which might generate some noise also. When you amplify the power, noise also gets added. Suppose you have a 1,000 kilometer link between two ends. You put the 3 amplifiers. So all 3 amplifiers will add some noise to the network. Noise is nothing but a power only, but it is unwanted power, you can say. Okay, which will impact your OSNR also. So once you travel from the distance and pass the components, your optical signal to noise ratio will reduce. But there are some requirements, like at least for this bandwidth to work, this much some amount of optical signal to noise ratio is required. Okay. So this is just a definition like SNR can be calculated based on the signal and noise. Noise figure is the component which should be lesser. I mean, always we want lesser. Amplifier will have these properties, how much noise figure it has or how much gain it can give. Okay, so we discussed about optical spectrum, right? Why we used this spectrum. So when you see here, right, there is ultraviolet, visible, infrared. So there are different bands here. In this band, we are using 1530 to 1565 C band, which is called C band, and L band is a 1565 to 1625. So these are the bands where attenuation is very low. So this is the reason we use these wavelength ranges in the optics. Okay, now we will move to the technology. So we saw about optical fibers, different impairments. Now we come to the DWDM, which is a technology like dense wave division multiplexing. So when we have to understand that, we should understand WDM. So WDM technology allows several optical channels to occupy a single optic fiber. So challenge here is what it is solving is we have already fiber is laid off between that different cities, right? So if we have to increase the wavelength, the challenge here, how can you carry the different, the more data within the same fiber? Okay, so this technology helps here, and it takes the different wavelengths, multiplex, and put it in a single fiber. Okay, so that you can carry the more data, more number of channels within the same fiber without laying an additional fiber. So here, the advantages are more channels per fiber, increased fiber capacity, increased service density, and solution for fiber constraint routes. So we can, so when we compare, right, this TDM versus DWDM. So the traditional one was TDM, the time division multiplexing, where we used to get that data and we divide the data into different time slots, time intervals. Okay, but if you compare the DWDM, here all signals arrive at the same time rather than being broken into the time slots. Okay, so time division multiplexing always focuses on the increasing the bit rate to increase the bandwidth. Here we increase the number of wavelengths. So we can have within that spectrum 1530 to 1565, we can have 80 channels of wavelengths. Okay, so 80 channels we can carry. Every channel can carry some wavelength. Every channel can carry some wavelength and some bandwidth. Okay, it can be 100 gig, 200 gig, 300 gig to 600 gig. Okay, so that is the advantage like DWDM gives in the single fiber, you can have n number of channels within the same network. Okay, so when we will go to the DWDM block diagram. So whatever topology I have shown you, right, this is similar to that only. So here what you see the box on the left side, which is the transmitters. So the transmitters is nothing but an optical output. Optical output can be of one framer ATN, and right side is the receivers. Okay, so there is a DWDM multiplexer which is taking all the wavelengths here, combining together and putting into the fiber. Okay, then there are three amplifiers you see in the network: power amplifier, line amplifier, receive preamp. So I talked about optical amplifier. When power gets reduced in the network, we need to amplify. Okay, so these amplifiers are having different advantages. Optical amplifiers, so that will provide some gain. So amplifier will provide some gain. So once you get all the channels together in one fiber, it carries amplifies in all the stages of amplification, and receiver will get all the channels together, and demultiplexes all the lambdas here and provides to the relevant receivers. Okay. So in this all this system, we have three components. One is the mux ponder, which is taking all the Ethernet inputs and converting into the OTN and putting the wavelength on it. Those wavelengths are coming to this DWDM multiplexer. Multiplexing, it is going on the amplifiers, amplifying, and is reaching to the receiver. So there are three components majorly: mux ponder, mux demux, and the amplification. The optical amplifier, what we saw in the network, right? There can be three type of amplifiers. So based on the requirement and distance, there is a very complex formula to calculate that optical power link budget. When we plan any link between two cities or any different places, right? So we have to plan the network based on the distances, based on the bandwidth, what type of requirement, cost, etc. So based on that, they will decide, okay, we have to put line amplifier, we have to put what kind of amplifiers and what distance. Okay. So amplifier is nothing but like just amplifying the signal. It is providing a gain. It should have low noise figure. Okay. Yeah. So mainly we have discussed about amplifiers. We have discussed about mux, demux, and mux ponder. Mux ponder is nothing but what we are doing in NCS 1K. NCS 1K has mux ponder and amplifiers. Okay, so NCS 1004, NCS 1002 is the our mux ponders. If you see this left side, right, so these are the outputs of mux ponder, and these amplifiers are nothing but a NCS 1001. Okay, what we will discuss in next topology diagram. Okay, so now when we talk, right, we are converting Ethernet into optical, Ethernet into OTN, then we are putting a wavelength and putting into the layer 0. So we should know the framer, right? Like we have a framer in Ethernet. So you put your data in Ethernet frame and carry. Similarly, when we have to go into the optical network, right, we should have some framer where we can put our data and carry only the optical network. Okay, so the technology called OTN is optical transport network. Okay, so we'll discuss about optical transport network. Then we will converge everything in one topology and just see how it carries, right? So why do we need OTN? Okay, so OTN overhead. So any protocol, right, which carries the traffic, that will have some overheads. So similarly here, OTN also some overhead OTN has, which is basically for operational and maintenance capabilities, and it is providing basically like troubleshooting purpose, right? For suppose you have some problems, right? So you will go to overhead and you will get the relevant alarms based on the overheads. Okay, so Ethernet, you might not have these many alarms what optics or optical network has, because optical network, we don't go within the data and we are not worried about the data within, right? We just rely on the overheads. If overhead bytes are correct, we don't have any alarms in the network. We consider the layer 1 physical link is up. Okay, so basically we are relying on alarms, errors, and trace messages. OTN payload is bit timing and protocol transparent. So any type of data can be carried on the OTN frame. Okay, any type of client signal. It can be Ethernet, it can be Sonet, it can be anything you carry. I mean, anything you insert, it can be accommodated within the OTN frame. OTN has an advantage of FEC. So FEC is nothing but a forward error correction. Okay, which we will discuss in one of the slide in detail. Forward error correction is used to improve the performance. Okay, so there is a procedure which will detect the errors and correct the errors within that frame, and it will give a better performance. The signal can go for the long distances. OTN is an integrated transport solution. Okay, so basically when we talked about OTN and DWDM, so when it is combined together, it makes a complete optical network. Okay, so it can be used for 40 gig and 100 gig, and next is it will be 400. So this is the layer diagram where we see like all the IP MPLS network. In the bottom you see LOODU, so which is nothing but a optical data unit on the OTN, and the last one is HOODUs, which is a higher order ODUs. So this is just a representation of the network where how do we carry the network, right? So if you see, right, higher order ODU networking is used when client throughput does not need further aggregation. So directly it can be mapped to the higher order ODU. Lower order ODU networking is used when sub lambda multiplexing is needed. So when we get that data into the lower order ODU, it further aggregates to the higher order by the multiplexing mapping. Okay, so the switching is always based on the like we can have the ODU level switching. Okay, so this is the layers when we see OTN client mapping. So you see, right, all type of traffic, IP, Ethernet, SONET, video can go here in the payload. So this is the OTN payload, which is very transparent. This is the header, which we will discuss in detail. And here is the FEC, which is forward error correction. Okay. And further, it creates an OTN frame. It goes multiplexed, and it goes as an optical channel here on the bottom, which is colored nothing but a layer 0 again. How it builds that OTN container. So when you have a client signal, can be anything 100 gigi, for an example. So 100 gigi client signal will come here. It will be encapsulated into the OPU, which is optical payload unit. So OTN has the 3 layers. One is OPU, then encapsulation is ODU, then further encapsulation is OTU layer. So once you add into the OPU layer, so here you will add some overheads, OPU, which will take care of your payload. And any alarm comes towards the client signal, it will tell you. And what kind of overhead you are carrying also, it will tell OPU overhead. Another encapsulation is ODU. Another encapsulation is ODU. So ODU overheads will be added here. So when we talk about end-to-end circuits, right? So the circuits will be ODU circuits. Then another encapsulation on top of that will be OTU, which is optical transport unit. So between two ends, if you have to monitor the link, so that is the OTU layer, and it will monitor the sections, different sections within the network. The OTU layer will be used. If you have to monitor end-to-end circuit, the ODU layer, and if you have to monitor the payloads, right? So then payload related things will be taken care by OPU overhead. So further OTU layer, OTU will be encapsulated into optical channel, which is an optical domain. And on optical channels, we'll have multiplex unit and the transport module further. So OTN will have different rates. Different rates. First one is OTU1. OTU1 will carry ODU once, if you see right here. For every corresponding OTU, there will be ODU. Okay, ODU1 is there, which can carry some STM signal, STM16 signal. If you want to carry 10 gigi LAN, so you will have ODU1E, which will be encapsulated in OTU1E. Similarly, for different client signal rates, we will have corresponding ODUs to carry and encapsulate further. So if you see on the bottom 100 gigi will be carried on the ODU4. ODU4 encapsulated in OTU4, and that OTU4 OTN channel will be assigned on wavelength and it will go into the DWDM network, so that your Ethernet is encapsulated in OTN and it is going via DWDM network on the wavelengths, on the light. Okay. So FEC, we talked about FEC. So that is a forward error correction. It is the last part of the OTN frame, which is improving the burr performance of the link. It can extend, maximum span of the link can be expanded to the 20 kilometers. And we talked about, right, we need regenerators, amplifiers within the network, right? So it reduces it, it gives a better performance, so you don't need that regenerators within the network. So that is also one advantage of FEC in the OTN. Okay, so the OTN frame structure. We discussed about the payloads, right? What all payloads can carry, that is under the OPU payload area it will come. We have overheads, OPU overhead, ODU overhead, OTU overhead, all are aligned together and it makes an OTN frame. Okay, so this one, yeah. So when we decode these overheads, you will have frame alignment overhead and multi-frame alignment overhead. So this frame alignment, when we have a network between point-to-point network, so the OTU layer we will have to monitor, right? So on this OTU layer, we will have to monitor these things like frame alignment and multi-frame alignments. Similarly, this section monitoring. So section monitoring also works on the OTU layer. Then whatever circuits we carry within the OTN network, all the ODUs will be monitored on the ODU layer overheads, whatever red one, and it will have a different segments also. Like for the international network, you will have a different carriers which is carrying the same circuit within the different network. So if one segment has the problem, so the TCMs, you see, right, tandem connection monitoring, there are 6 levels of TCM which can help to debug within that segment in case any problem comes. So in the overheads, section monitoring and you see PM, right here, so that is a path monitoring. So these overheads will have uh, different traces. If we are sending from one place to another place, right? So we can send some trace message so that we will know, okay, that is the correct point we are reaching. And there are some bytes APS, if you see, right, that is used for the protection switching. So if you have some working and protection path switching, right, so that is done via APS. So these overhead bytes will be used for this all operational and maintenance purpose. GCCs are used for the communication, basically the whatever communication within the layers. So section monitoring will have GCC for OTUs, and here audio overheads will have GCC 1 and 2 for the communication channel. The last one is OPU overhead. So OPU will carry the data basically, right? So OPU payload will have the type of payload I'm carrying. How would I know like what type of payload I'm carrying? Suppose Ethernet or any Sonet or anything. So it will tell within the bytes. There is a byte called payload type PT. It will tell what type of payload I'm carrying. Because for the L1 technology, right? This is a we don't go within that data. We just rely on the overheads, and we are just a physical layer. We just take care of the physical layer. So on the physical layer itself, we have to monitor the alarms, errors, and performance of the link. Okay. So yeah, this is the DCI topology what I have shown in the beginning, right? So this has a mux ponder. What we do in NCS 1004. Then there's a mux demux. So this is called MD48, right? So we can carry here maximum 96 channels within one network. Within the we whatever spectrum we have, right, we have to divide, and there is a spacing between that wavelengths. So if you are using 40 wavelengths, you will have 50 gigahertz spacing. 80, suppose you are using 80 wavelengths, you will have a 50 gigahertz. You are using 100 gigahertz spacing, so there are more space between the two wavelengths. So you can use the less number of wavelengths. So based on the spacing, you can use the number of channels within the DWDM network. Okay, so we have the two topologies. One is this one, where we take the inputs from Nexus, ASR9K, and Freta, and it goes via the mux ponder, which is NCS 1004. It goes via mux demux, and then amplifier. So amplifier is nothing but an optical amplifier, which is Mystic. Okay, so here we will have an amplification, and we have two paths of protection. So we provide the protection here, not on the mux ponder, but in the amplifier. Okay, so the network goes in two paths, working in protection. Amplifier. Okay, so these are the three components basically. Second topology, what we have is NCS2K. So NCS2K is another product line for optics, which has the ROADM technology. So what we discussed about the DWDM technology. So in DWDM, what happens? You have the predefined wavelengths here within the spectrum. For example, 1530 to 1565 wavelength, right? So you have a predefined wavelength on every port. Whenever mux ponder output will come, the fiber will connect to that wavelength, fixed wavelengths. Okay, so you have some limitation. You cannot, it's not flexible. So you can carry the fixed wavelengths, number of wavelengths. But here in the ROADM, right, in the ROADM, it allows us to reconfigure the wavelengths. So, and it has the new concept called flex. So in the flex spectrum, within the same spectrum, 1530 to 1565, right, you can use uh, more wavelengths based on the flex. Okay. You are not having a fixed channel spacing between the two channels. Based on the bandwidth, you can use that spectrum space. Okay, so this 2K network, what you see in between, right? So this is, here we have a GMPLS switching, that is a control plane switching. So whatever lambda travels, right, from one path, it has a 1 plus R protection, 1 plus 1 plus R, and different type of protections we have in the GMPLS. There are two types of topology. One is amplifier with working and protection PSM. Another is with NCS2K GMPLS switching. Okay, so, and in NCS1K we mostly test point to point because it is for the DCI. Now we are so mostly we are using DCI in this profile. Another one is regen. So this multiply, like this mux ponder can be used as a regen also. So in between we can have another node which will regenerate that signal, and further it can go to the far end. So this is another topology diagram in detail, which will tell, if you see the green part, all the inputs are coming. This is nothing but a Bossog line card. This is a mux ponder. So if you see one line card here, the traffic is coming from the aspirant to the devices, routers and switches, and this outputs are going. So there is one line card which has 12 client ports, which is a Ethernet 100 gig QSFP ports. So from, if you see like 2 to 7, right, this input will come to these ports and it will go via port number 0, which is a OTN port here, which is a coherent port. So that port 0 will get all the data on OTN and it will put it on the mux demux, which is another DWDM this part, mux demux, and it will go to amplifiers. So the amplifier here, the EDFA is written, right? So the optical amplifiers are two types. One is EDFA, another is Raman. So we are using EDFA here. So the topology diagram is showing clearly like 6 client ports goes to one trunk port of 0 and multiplexed passing via PSM, which is a protection switching module. From the protection switching module, you will get two outputs. So two EDFA will get this output and it will go via one fiber spool, reaching the far end of the EDFAs. Again, that PSM get back to another mux. So this is the point-to-point topology between two line cards. Yeah, now I want to discuss. I want to tell about the NCS 1004 platform. What all segments it works, right? So right now, what we discussed is metro. There's another segment will be long haul. Now we are approaching. Another is submarine. So the same like BOSOG will be used for submarine applications. What is the BOSOG advantage is it gives the high, it has a high density, high baud rates, higher order modulation. So modulation is another technique. What helps us to achieve that bandwidth. Okay, so modulation is nothing for the simple terms. Modulation is just a packing of the data within that symbol or within that waveform. Okay, so how much dense we can pack the data, we can get the more bandwidth within that same port. NCS 1004, this is the NCS 1004 picture. So it has the 4 line cards, which like every line card has a 12 client ports and 2 trunk ports. So we get overall like every line card can support maximum 600 gig of bandwidth. So every line card gives you 1.2 T. So overall one box gives you 4.8 tera bandwidth. Mainly the advantages here is within the less space you get the more bandwidth to the data centers. Okay. So this is the mux ponder 1004. Another one is an amplifier, which is the NCS 1001. We are using in the network. So this is another like point-to-point metro DWDM network. It has a protection and unprotected topology. Optical performance optimized for high baud rates and higher order modulations. It has a capability of OTDR, which is an optical time domain reflectometer. So in case any fiber cut happens in the network, this product can shoot the laser and based on the uh, reflected light, right, it can calculate the distance on what distance fiber cut happened. Next is NCS 1002. This is another mux ponder. So the first one we call it BOSOC NCS 1004. This is a Mystic. NCS 1002 is a Roscoe, which is the first mux ponder what we did in NCS 1K family. So here again, like we have similar kind of thing. Only the bandwidth is less. Like overall box capacity is less. Here we use CFP DCOs, which is just electrical to optical conversion we use. Okay, so Roscoe, another diagram we have. So it has trunk ports can be configured on the 100 gig, 200 gig, 250 gig. So every trunk port can be, it can give 250 gig of wavelength. So overall box capacity is 2 TB. So I think that's it on the product line. I have some backup slides what I can to discuss. So when we talk about amplifier, right? So amplifier has two types. One is EDFA, another is Raman. So we will discuss about EDFA here. Here how we amplify the signal, right? So once the signal enters into optical fiber, there are laser pumps used. Laser pumps used within that wavelength range to pump to amplify the signal, right? So this all process is done by a like stimulated emission and spontaneous emission, spontaneous and stimulated emission. Okay, so in this process, there is some noise also generated, which we discussed. Like in the amplifier, we should have a less noise figure. So if you see in the input, right, the signal is signal pattern and output. The output signal is amplified by the laser pump. Okay, so here optical amplifier advantages are there is no an optical, right? So there is no optical conversion here for amplification, and it is independent of the data rate. Amplification is independent of the data rate, and it has a flat gain to all the channels. So number of channels you carry via the amplifier, you will have a flat gain. Okay, so this is about the optical amplifier. Any questions you have on this content?
So Ankur,
Hmm.
in your system test, or when you do CVTs, how do you simulate those lengthy fiber cables, and how do you introduce those uh, what you say that means the decrease in that signal and all these those parts? Do we use some additional devices to do that?
Yeah, so we have fiber spools, right, to simulate that long distances. Mostly, what we have is 25 kilometer, 50 kilometers, 75 kilometer fiber spools in the lab. So we insert those and uh, performance testing, right? When you talk about L0 testing, right? Mostly we have all the performance testing happening in Italy lab. Okay, so there is a device called OSA, so optical spectrometer device, right? It will be used for the these properties testing, right? Whatever we discussed, right? L0 testing. Here in our optical CVT, what we do is all the XR related testing and uh, all the traffic, data path, whatever alarms we discussed, right, on the overhead side. In the data path, we will test all the errors, alarms, different kind of triggers, right, in the system. So you will have all the XR triggers, process restarts, reloads, CPU extractions, and then we will test all these recoveries and effects of these triggers on the network. Uh, how our traffic recovers, or there should not be any impact on the performance. This is what we do here in the our state lab.
Okay.
So, Ankur, on the client devices, what kind of features you enable from the line perspective?
On the client devices, see, we have switches and routers, right? So on the client devices, we have port channels on the Nexus. We have FRETA, right? So FRETA has a MPLS traffic input, but we are, I mean, from the Muxponder perspective, right? We are not that worried of different configuration on the client side. But yeah, we have a protection port channels, right, on the client side Nexus, and MPLS traffic on the FRETA.
Okay. You also have some kind of dampening configuration, link dampening on the client side, and test the flapping of your optical network and see how that client devices are behaving.
Yeah, so we test convergence basically when we flap the link, right, or For an example, my trunk port flaps for some fraction of millisecond, right? In that case, how the client port will behave, and it will impact to the peer device, whatever interrupt device, right? So in that case, we test that convergence.
Okay.
Ankur, all this testing, we are using the one type of cable. Is there any play with the cable kind on this? There is any difference which you are using single core, multi-mode cable, single mode cable? What is the exact implementation? See, these are the optical replication and amplification techniques which are using it. What about the cables? We can use
Yeah,
any kind of
mainly we have two type of cables, right? Single mode and multi mode. So for the all the optical operations, right? Single mode cable, what we use, right? Which is commonly used in single mode fiber for the all the OTN side connections. Okay, and based on the pluggable also, right? We have different type of pluggables like 40 gig SR4, right? In that case, we use multi-mode cable for Ethernet inputs. And if we have a LR4 long range, so we use single mode. So all the long distances, we have to use single mode fibers.
And how do you calculate? How do you calculate the capacity of that these user signals? Right, you have a max. How do you calculate how many? See, every port will be connected to different DCA, different data centers. It will be like how much data can carry. How do you calculate those information? Maybe one cable has one input has more bandwidth utilization, another is less. Have any kind of such a limitations. Power can this much data can be transferred via this port. Those kind of limitations there, or
Mm, no, I think this kind of limitations are not there because these are the fixed ports. Like 100 gig is the client port capacity, right? And based on my configuration, right? So for an example, I configured my mux ponder like my client ports are 100 gig and my trunk port can be 400 gig. So the capacity will be limited, right? When I can carry only 4 clients via my mux ponder in that case. Like 400 gig clients can connect to my mux ponder, and because I have a trunk capacity of 400 gig, okay, of OTN. So based on that,
okay.
capacity will be limited.
How do the node is getting know that only 100 gig will be coming? Just I want to like because all the things are OTN frame, right? So we'll have any fixed size of frames for that. Like if we have different headers, those things is fine. How the node is good know that there is 100 gigs coming on this port, like instance, how it will be divided the allocation bandwidth. Those is be like it is under up to our configuration level, or it will be done automatically on the optics.
No, no, not on the optics only. See, when you insert the optics, right, any type of optics, so our box has that alarm, right? If our box supports 100 gig Ethernet, if you insert 40 gig optics on that, right, it will give you alarm like pluggable mismatch. So the user will know, okay, this optics is not supported. So we have a certain list of optics which are supported for different bandwidths. Okay, like in case of NCS 1004, right, we have only one type of client support. So like 100 gig is the minimum client support. So you have to insert 100 gig pluggable only. So once you have 100 gig pluggable inserted, then only port will come up. Otherwise, it will be down only. So user will know, okay, the controller is down. So you should be using the right bandwidth size pluggable and configuration.
Okay, got it. Got it.
Yeah.
Yeah, this main purpose is OTN. This OTN main purpose is only for DCI, data center interconnectivity, or we have any other backhaul also they're using it?
No, not only DCI, it is getting used in all the profiles, like service providers are also using, and it has switching also, right? So in Metro DCI, the switching requirement is not there. So we are using point to point, but for service providers also it is being used, and for the even the long haul network also, right? OTN is being transported on the DWDM.
Okay. Okay, because DWDM specific optics are available the router itself, right? So, and since we have a set of optics which has supported 100 kilometers, 80 to 100 kilometers, so will the customers purchase these kind of solutions even it is more costlier than what the optics are?
You're saying the router has that DWDM port?
Yeah.
No, but I think that capabilities and like whatever data path we have, right? So these mux ponders are not having. Basically, the selling point here is the density only. So the modulation and the performance, what mux ponder can give, right? I don't think so right now. Cisco, right, within the router have that capability.
Yeah, that is true. Thanks, Shankar. Thanks.
So these slides are very basic. Okay, if you see right from the optical person perspective, right, these slides are very basic. I just kept it basic because the audience is different, right? Not only optical audience. So just to get the feel of basics, then if we want to explore further, right, I think we can have a detailed session on one particular topic also. Any more questions here?
Folks, any more question on WebEx?
No, Anchor on my side. Like, yeah, thanks. Thanks for your time.
Thank you. People like us who know very little about this opticals, uh, this was a good fundamental course for us. Yeah, will help surely.
Okay. Yeah. Thank you.
Awesome, Ankur. Thanks for taking time out to present. I see a lot of audience as well. So hope everyone benefited out of it. Thank you so much.
Thank you, guys. So we are closing if no more question. Thank you.